Okay, form factor. Next is the form factor. Form factor is the comparison between SCR RMS current compared to SCR average current. So this is our form factor. So the curve already compared between the two values. It shows that when the alpha increase, the difference between RMS value and average value will increase. The difference. So this is important when we want to select or want to set limitation of our current that can pass through any device. Let's say the SCR, enter the SCR. If you need to trigger the SCR, and with the form factor at certain values, so we have to limit the current. Let's say the SCR can withstand up to 50 ampere. So with the certain form factor, we have to maybe direct the values down 40 ampere, 30 ampere, like that. Or we have to choose any other device that can tolerate the certain form factor. Okay, SCR form factor. Then what's next? Load power. The load power, maximum output power. So how much the power being absorbed by the load. So at this P output normalized. See? P output normalized. At 40 degrees, the load power here, P output maximum is equal to V in RMS squared. This is my calculation. Okay, V RMS divided by the resistance value. Okay, if we refer to our P curve, P output maximum, so the maximum load power maximum is means that how much the capability or the power, maximum power, P max, not the P at 40, not at 40 yet, but P max. P max happen when our alpha we trigger at 0. So means that this is the point of alpha. So P max is here, and P output normalized should be right here. So 1 per unit, 1 per unit times so 1 per unit means that V in voltage here is maximum squared over R, so 2880. But at maximum power equal, so same goes here. V in RMS, we found it to be at alpha equal to 0 is 240 volt. Yeah, V in RMS, V in, V out, maximum normalized, V in RMS. No, V in is not altered at any alpha. V in is still 240. Okay. V in is stick at 240 times I RMS at alpha equal to 0. This is I in maximum normalized. I out. Yeah, I in RMS normalized 0.7. So what? 0.71. Yeah, almost 0.71 or 0.707. So times 240 by 20, so we get 2880. Okay, this is from P curve. Maybe we get a little bit higher, but still within the range. So means that this is the maximum output or maximum the load can absorb. But at this alpha equal to 40 degree, so the output at this point is 0.94 normalized. So the output power at this point is P output normalized times P output max. Maximum 2880 normalized at 0.94. So at this point, at alpha equal to 40 degrees, the load will absorb only 2707 watt instead of 2880 maximum it can absorb at alpha equal to 0. Okay, understand? Then the input volt ampere. Input volt ampere. IN RMS at 40 degrees. IN RMS. This input volt ampere. So the IN RMS we have calculated just now in page 32, which is 11.54. So you can see here IN RMS is 0. And the normalized factor of 0.68. So times the V peak divided by the system value. So we shall get 11.54 ampere. So the volt ampere is equal to V in RMS times R in RMS. V in RMS is 240. So we get 2769 volt ampere. This is our input volt ampere. So the ball factor we can divide between the P in that we calculate. If we refer to the curve, it can show here already 0.97 or around 0.96 like that. 9697. But through calculation, we can divide 2707 that we have calculated compared to the 2769 that we have found latestly. So 0.9977, almost 9.8, 0.98. Okay, so that's the input power factor. So what about the SCR maximum forward voltage and also maximum reverse voltage? This one is required when we want to decide in terms of our rating, voltage rating, current rating of our SCR. So which part is suitable for our design. So how to calculate SCR maximum voltage, forward voltage. So during forward voltage, so V in peak divided by 2 sine alpha. And sine alpha. So we should get forward voltage of 109.3, and maximum reverse voltage, holding voltage or blocking voltage, so is the maximum peak values of our source, and so 340 volt. That so means that if we selecting the device to be operated in our converters and our thyristor, so means that it should withstand at least 340 volt, and maybe you have to find a 400 volt because we have to cater the spike. Maybe you switch on, you will have a spike. So 400 volt or 600 volt, and means that if you use the 300 volt rating, so you might damage, and you will damage your device during operation due to spike. And this is the spike. If you choose a higher rating, so you might save in terms of the issues of voltage spike to the device. This is in terms of device selection characteristic. Okay, that's all for the PA curve usage inside our full bridge rectifier converter. Means that once you get this kind of scenario, you have to characterize each of every parameters that remains here using PA curve. V, I, P of output, V, I, P of input in terms of average RMS, peak, and also voltage, current of our device. Okay, this is the simple rectifier circuit. Later maybe we dealing with the buck boost converter, and other converters. So the same approach applied. Load point of view, source point of view, and also the device point of view. For the time being, we are not considering yet in terms of how to control or how to design the controller for the converters, because the one they belongs to other subject, electrical drive control. Okay, that's all for the discussion of full bridge rectifier. Thank you very much. Assalamualaikum.